In the last class, we had learned what is called the rank nullity theorem. So, let us recall what it was. A was an m cross n matrix. Then it said that rank of A plus dimension of null space of A was equal to n. All right. N is number of columns of A, or which was number of unknowns or variables. All right. So, this was called nullity of A, and this by definition itself is a rank. Fine. So, this is what the idea was, and to prove it, the idea was that you start with a basis of null space We took it as a u1, u2, uk. Dimension was, or the nullity of A, we took it as k. Fine. Extended it to get u1, u2, uk, comma uk plus 1 to un, a basis of Rn, because I am looking at Ax. So, I am looking at this. So, Rn is coming into play, and to get the column space A, which was nothing but Ax, x belonging to Rn, we saw that this is same as linear span of A of u1 till A of uk, A of uk plus 1 till A of un. But these vectors are 0 because they belong to the null space, u1 to uk belongs to null space. So, this was nothing but A of uk plus 1 till A of un. So, we showed A of uk plus 1 to A of un is a linearly independent set. That is important. And to do that, we consider the system of linear equations. Then we showed that there is a certain vector. So, there was a certain linear combination of uk plus 1 to un, which belongs to the null space of A, and that implied a contradiction to u1 to un, this being a basis of Rn, and this implies the linear combination, the coefficient must be 0, implies. So, this implied linear independence of A of uk plus 1 to A of un. We will again come back to it when we will go to linear transformation. We will use a similar trick to prove a rank nullity theorem there, but I would like you to understand it nicely. Fine. This is the one which relates rank with the nullity, and hence it says that go back to the system of equations. There you have got certain nice results coming into play, that if the rank is k, then there are n minus r linearly independent elements in the null space of A. Fine. Let us proceed further with the fundamental spaces. So, we had looked at this example. So, let us write that example again. All right. So, I had the matrix A. From there we had gone to RREF of A, and RREF of A was 1 0 3 minus 5, 0 1 minus 2 3. This was the RREF of was, and A was equal to 1 1 1, 1 2 minus 2, 1 minus 1 7, minus 2 1 minus 11. All right. So, I would like you to see that that when I am solving the system, so look at this null space of A. So, null space of A is all A x such that all x belonging to R n such that A x is 0. So, what exactly we are doing? Let us understand that. So, I have this first row, second row, the mth row of A. This is my A and my x is x1, x2, xn, or basically x itself. Fine. This is a matrix of size m cross. Yeah, what is the size of this matrix? 1 cross n. Each of them is 1 cross n. So, I can write it as A of this times x, this x. Fine. So, let us look at this for example. So, this was 1 cross, there is only one row, there are n columns, and I am again multiplying by n cross 1 because x is n cross 1. So, I am getting it is 1 cross 1, so it is a scalar quantity, and we are saying that this is corresponding to x, which is supposed to be 0. So, we are saying that this implies this is 0, this is 0, and this is 0. Fine. So, what are these vectors? So, let us try to understand what are these vectors that I am talking of. Fine. So, in general, if I am got here in this example, if I look at here, if I write here x, y, z, u here, then we are looking at the first row as x plus y plus z minus 2u is equal to 0. All right. Or in some sense, I am looking at, look at this vector 1, 1, 1, 2, x, y, z, u. I have got these two vectors, and we are looking at what is called the dot product of the. So, we are looking at the dot product of two vectors. So, recall that in R3, if you have vector x which is x1, x2, x3, y was y1, y2, y3, then the dot product of x and y was x1, y1 plus x2, y2 plus x3, y3. All right. That was the dot product. So, in place of 3, I have got 4 components here. In general, I have got n components. I am looking at Rn. I can still define my dot product as component wise. So, if I have got x as xn, y as y1 to yn, I can define my dot product x dot y as x1 y1 plus x2 y2 plus xn yn, which is also equal to, if you can see here in terms of the matrix notation, it is also equal to x transpose y or y transpose x, whatever way you want to write. So, when I am looking at x transpose y or y transpose x, at the back of my mind I have a dot product with me, and there was a notion of dot product which said that they also give us what are called angle between two vectors. So, dot product gave angle between two vectors. So, what do I mean by this? So, given that x and y are two vectors in R3, if theta is the angle between them, then cos theta was equal to x dot y divided by length of x into length of y. All right. So, this I am writing it as length of x, and this is equal to a square root of x1 square plus x2 square plus x3 square. Is that okay? Fine. And we said that x and y are perpendicular or orthogonal if x dot y was 0. Fine. So, here in this notion of matrix multiplication, it turns out that x transpose y is 0 if and only if x and y are orthogonal. Fine. So, I can talk of perpendicularity of things, all right. So, what we see from the last part is that what we had seen was that if I look at, so if x belongs to null space of A, then first row times x was 0, second row times x was 0, and so on. It means that these rows implies that all the rows of A are perpendicular. Why? Because the dot product is 0. All the rows of A are perpendicular to the vectors in null space of A, all right. So, let us go back and see whether this is true. So, let us look at here, fine. So, the null space of A is going to consist of, so what is the null space of A here? So, null space of A was, in this example, it was all x, y, z, w such that x plus 3z minus 5w, 5u is 0, and y minus 2z plus 3u is 0. So, you can see here that 1 plus 3z minus 5u is 0, y is 1 here. So, 1 times y minus 2 times z plus 3 times u is 0. Just multiply with this also, you can see that 1 is here plus 3 is 4, all right. So, z and then 5 times u is 10. Null space of A, just a minute. So, where is column space? Oh, column space is this, sorry, fine. So, check that they are 0 here as such. So, just look at this here, all right. You are saying the null space is here, take a solution of this. So, take x naught to z naught to y naught belonging to this. So, therefore, I think I have not written in terms of this matrix form, but anyway. So, for you, so that you have a clarity here. So, from here if I want to write here x, y, z, u is equal to x is minus 3z plus 5u, y is 2z minus 3u, z and u. So, this is same as minus 3, 2, 1, 0 with respect to z, and then with respect to u 5 minus 3 u 0 1. So, check that now everything is nice, that minus 3 plus 2 plus 1 is 0, that is this part, minus 3 multiplied to the first component, 2 multiplied to the second component, 1 multiplied to the third component, and 0 multiplied to this is 0. Similarly, look at here, 5 multiplied to the first one, minus 3 multiplied to this is 2, 2 minus 2 is 0, fine. So, I would like you to see that each of them is 0. So, the null space of A is generated by these two vectors. So, these two are the basis vectors, fine. So, I am going to use this idea of perpendicularity in the next thing. So, this is called the fundamental theorem of linear algebra. So, let me write it down. So, theorem, this is called fundamental theorem of So, I will not be able to prove all of them because of certain reasons, because we have not yet understood what is orthogonality, but I will just state it so that you have a picture of this. So, A is given to be an m cross n matrix, m cross n matrix with real entries, fine. Then what happens then? 1 dimension of null space of A plus dimension of column space of A is n. This was the rank nullity theorem. Two, null space of A is equal to, look at the column space of A transpose, all right, look at this thing, what is called perp, for perpendicular or orthogonality. We just saw, if you remember, that what is column space of A transpose is nothing but row space of A. So, we are saying that every vector in the null space, so we are saying that every vector in the null space is orthogonal or perpendicular to every vector in the row space of A. All right. Why? Because why I am saying this row space of A, every vector, because row space, if I want to look at, is generated by the linear span of the different rows. Sorry, it is A here. Fine. So, the row space is generated by linear span of the rows. We already saw that A times this of x was 0, all of them was 0 for us, isn't it? This is what we already saw. So, this says that null space of A is perpendicular, is orthogonal to row space of A. So, again look at it nicely, fine. Then the another version of this is, this I am looking at A and A transpose. I would also like to look at what is null space of A transpose and the corresponding here. So, null space of A was related with column space of A transpose. So, it should be column space of A transpose gets A, because A transpose transpose is A, and then I have to look at perpendicular here, fine, which is same as, so null space of A, I am going to null space of A transpose, column space of A trans to column space of A perpendicular. Is that okay? That is what I am doing here. So, this is all, this was left null space, all right. And the third one is dimension of column space of A is equal to dimension of column space of A transpose, all right, fine. So, this part tells you, let us try to understand, dimension of column space of A is talking about number of pivots, all right, number of elements in the columns. It is talking about linear independence of columns. This is talking about linear independence of rows. What we know is that this gives us the row rank of A, fine. This will similarly give, by definition, this is nothing but the column rank of A, which is same as column rank of A. So, we are saying that column rank of A is same as the row rank of A. Is that okay? And how do we prove it? We prove it using these 1 and 2, you get the result directly, all right. So, just let me write the third part, second part also will come. So, let me write the third part first. So, third part, if I want to look at the proof, first is already proven earlier, second part we have already seen some part, in the sense that we have already shown that every row of A is perpendicular to the elements of null space, and therefore, the linear combination will also be perpendicular, fine, because if x is perpendicular to y, z is perpendicular to y, then x plus z is also perpendicular to y, all right. So, you can use those ideas to prove yourself. I am not want to waste my time there, try it out yourself. So, I am just trying to prove the last part, that is that row rank is same as column rank. So, now let us look at dimension of column space of A is nothing but the rank nullity theorem, it is equal to n minus dimension is this. So, dimension of null space of A, all right. Dimension of null space of A plus dimension of column space, which was the rank of A, column rank, is equal to this by the rank nullity theorem. So, this is because of the rank nullity theorem. This I can also write it as n minus dimension of null space of A. We saw that, yeah, what was null space of A? The second theorem we had, that null space of A is equal to, look at the column space of A transpose, all right, go back, null space of A was equal to column space of A transpose perp, all right. So, null space of A is column space of A transpose perp, so A transpose perp, fine. So, it is same as column space of A transpose perp. Perp means perpendicular. So, if x is perpendicular to y, things like that. So, we would like to know what is the dimension of this. So, what should the dimension of this? So, can I say that? So, let us look at this part to understand it better. So, suppose I give you, so suppose u1, u2, ul is a basis of column space of A transpose. Suppose I give you this, fine. So, A transpose I am looking at is n cross m matrix A transpose, fine. So, each column is of size, what is the size? N, things like that. So, now if this is a basis, can I find, so can we find orthogonal vectors? That is the question, first question. 2, if yes, how many of them? 3, what is the number of linearly independent vectors orthogonal to column space of A transpose, because you are looking at this part, all right. So, I would like you to see that this is again a function of n itself, because each of the columns are of size, column space of A transpose. If I look at A transpose, all the columns are of size n, therefore, it is a vector of n. So, it will be n minus itself, because column will get transferred into column itself. Is that okay? So, it will be n times dimension of column space of A transpose, n cancels out, I get this as dimension of column space of A transpose, all right. So, I have not been able to give you the idea of this part, that how do I go from here to here. I would like you to try it yourself. For example, if you already know, for example, if I am in R3, I give you two vectors 1, 1, 1 and 1, 2, 1. These two are linearly independent. Then there is a unique vector orthogonal to them. So, we are saying that this is unique, means there is only one. So, it is 3 minus 2. 3 is the dimension of R3 and 2 the vector 2 that we are giving here. So, this is what we get 1. If I give you only one vector 1, 1, 1, then there are two vectors which are linearly independent, which are perpendicular, 1 minus 1 0, and another vector is 1 1 minus 2. Both of them are perpendicular to this vector. So, again this number is 3 minus 1, which is 2. So, this number comes from that idea itself. I cannot prove it at this stage, because I have not yet talked about inner product, dot product and so on, but in R3 you already know. So, if you go from R3 point of view, you can see that everything makes sense and you can get it, fine. So, this is what the fundamental theorem of linear algebra is. So, what is the fundamental theorem of linear algebra? There is a notion of what you call the rank nullity theorem, that you already understand. The second part says that you can relate null space with the row space in some sense. So, you are not looking at row space, you are looking at the perpendicular, the vectors which are perpendicular to the row space. Look at here, the vectors that are perpendicular to rows, all right, fine. So, this is important. And the third one was nothing but relating the two things. Is that okay? So let me write this in terms of a diagram so that there is more clarity on it. Fine. So let me make a diagram. So what we have, I am going to write Rn here, which was the domain space. I have got Rm here, which is the column space, and I have a function f, so that f of x was Ax. Fine. A was m cross n, x is n cross 1. So I get fx, which is an element here. Fine. So I would like to write like this here. I have something here. This is perpendicular here. Fine. So let us look at what are the subspaces. I have what is called the row space here, row space of A, which was nothing but column space of A transpose. Fine. Recall again nicely, A is m cross n. So each row has n components. Fine. Each row has n components. So the row space is a subset of Rn. Fine. Now it was perpendicular to what? So column space of A transpose was perpendicular to the null space of A. So let me write the theorem again, statement for you, so that there is a clarity that null space of A was equal to column space of A transpose whole perp. Fine. Similarly, you have there also. Fine. So row space of A was this, and they are here as such, and the dimension of row space of A was R. Fine. You have null space, which is perpendicular here, and here again dimension of null space of A is n minus R. Is that okay? If I look at here there were rows, because each row had how many components? N components. Now I have columns. How many components are there in the column? So each column of A has m components, and therefore a column space will be a subset here. Fine. And dimension of column space of A is also R. Fine. Important, again there is a perpendicular here. So orthogonal, orthogonal or perpendicular. Fine. And you have column space here, you have row space or column of A transpose. So from A transpose you went to A. Similarly from A we will have to go to A transpose. So I have to go to null space of A transpose, and dimension of null space of A transpose is m minus R. So here it is m, here it is n. You have to be careful that there are two different numbers here, even though at the top there are same numbers. Is that okay? So this is the picture of fundamental theorem of linear algebra. You need to understand it so that you know which is perpendicular to what and what you can do, what you cannot do. All right. So if you see here, this dimension is R, this dimension is also R. Therefore, you can get a unique function from here to here. So whatever vector you get here, the number of vectors here, it has got R component R. So if its dimension is R, it means that there are R vectors in the basis. There are also R vectors in the basis. I should be able to get from one to the other. All right. So there is a unique map. This part I cannot have uniqueness because there are different sizes, there are different issues that will come into play. But at the top part, from column space to row space and row space to column space, I can have a 1-1 map, and therefore that also tells you that row rank and column rank should be the same. Fine. So as a final part, I would like you to relate these definitions that we have already done. So exercise. So I have an m cross n matrix. A is m cross n. Fine. So, the following statements are equivalent. I will not proving them, but I would like you to understand them. Rank of A is k, B, there exists a set of k rows of A that are linearly independent. See, so k rows of A are linearly independent means you are looking at column space of A transpose or row space of A, their basis is that, fine. There exists a set of k columns of A that are linearly independent, fine. Again the same thing, you are going to from A you can prove B, from B you can prove A, as the fundamental theorem says. Again A proves C, C implies A, you can do that yourself, and they together imply you that dimension of column space of A is k, dimension of row space is also k, E, there exists a k cross k submatrix of A, submatrix B of A with determinant of B not equal to 0. So, k cross k here it is very important, and every k plus 1 cross k plus 1 submatrix of A has determinant 0. I have not proved it, but you can look at the RREF. In the RREF what happens is that you are going to get the matrix of the type IK. So, if I not exactly the RREF, but look at PAQ, so I can write it as this. So, recall that there was this theorem which said that given any matrix A of rank k, rank is k, I can get an invertible matrix P on the left, Q on the right, such that I get IK 0 0 0, and therefore, it says that if I take any k plus 1 by k plus 1, the determinant has to be 0, and there is a k by k here which is non-zero, which has non-zero determinant, all right. So, this is what this language is about, relating this with this, because determinant of PAQ is same as determinant of P into determinant of A into determinant of Q, fine. P and Q are invertible, so determinant of P is not 0, determinant of Q is not 0, so they do not play a role, everything is being played by this, is that okay? And accordingly you get those parts, fine. So, somehow the matrix multiplications make sense here. F, there exists a linearly independent subset B1, B2, Bk of Rm, all right, such that Ax is equal to Bi for 1 less than equal to I less than equal to k is consistent. So, there are k choices in Rm. There is a k dimensional subspace for which we have a solution. This is what it was about, saying that I have a solution here, all right. So, there is a k dimensional space here for which I have a solution here. Is that okay? Fine. E, F, G, dimension of null space of A is n minus k, fine. Similarly, you can have another one which is dimension of null space of A transpose is m minus k, all right. So, all of them they are equivalent condition. You can prove one. So almost all of them can be proven using the fundamental theorem because of this diagram that we have got here. Everything follows from here if you have understood the definitions. The only problem is looking at this part, which is about determinant. They follow from here and some properties of determinant that I have not told you. So I would like you to understand it. This is the most important part that you need to understand. Is that okay? So try that out yourself. That's all for today. Thank you.